Hello, everyone. I'll be sharing about my final year project on protecting neural networks from adversarial attacks. The background of this project is that machine learning has become extremely popular in the recent decade, with a wide range of applications from recommendation systems to generative AI platforms such as ChatGPT. And the popularization of machine learning has led to the introduction of a new framework known as machine learning as a service, where a software company such as Amazon provides a trained model to the client, adopting a pay-as-you-use model. The machine learning model provider has the technical expertise as well as vast amounts of data and computing power required to build and train the model. This model will be deployed onto the cloud, and the client can access the model and even fine-tune it using freshly collected data. However, the sharing of machine learning model introduces a new concern regarding the protection of intellectual property rights of the model. Previous studies have shown that neural networks are vulnerable to model extraction attacks, where an adversary attempts to steal the model. They do so by first extracting information on the architecture of the model, which includes the depth of the neural network and the types of layer used. They also try to extract the specific weights and biases of the neural network. Hence, the objective of my project was first to watermark the model to allow verification of the legitimate owner, then to lock the model to restrict usage to authorized users only. Lastly, I aim to investigate how locking different layers in a neural network might allow for watermark preservation even after incremental learning. For the scope of this project, image classification datasets are used, namely MNIST, Fashion MNIST, and CIFA-10. And for each dataset, it will have its own convolutional neural network. So, what is watermarking? Watermarking is to take a small set of altered data and use it as the trigger set. The trigger set is known only to the legitimate owner of the model. So, for example, if I want to prove that I own a certain model, I will input the trigger set, and if the model identifies it as a trigger, I can prove that I am the legitimate owner of that model. This project experimented with 3 different types of triggers. One method is to embed meaningful content into the image, which in our case was to overlay a text onto the image. Another method is to embed Gaussian noise onto the image, and the third approach is to use images from an unrelated dataset as a trigger sample. Next, locking means to encrypt the weights and biases in the neural network such that a locked model will not produce any meaningful output. Hence, in the unfortunate event that an adversary manages to steal the model is useless to him unless he has the key needed to decrypt these parameters. I will now give a quick overview of the experimental procedure. First is to prepare and process the data to generate a trigger set, a primary training set, and a set for incremental learning. Using the trigger and training set, I built and trained a watermarked model. This model is then encrypted using a key before undergoing incremental learning. Finally, the updated model is unlocked using the key and evaluated based on its test accuracy and watermark accuracy. My project covered a wide range of experiments. For each dataset, I experimented with all 3 trigger set designs. The pre-training to incremental learning data split ratio is also varied. Lastly, various combinations of layers are locked, with the underlying principle of locking at most half of the total number of trainable layers. Experimental results show that the trigger set with meaningful content embedded in the images provide the best overall performance in terms of watermark and test accuracy. However, there is no silver bullet to watermark preservation. Each dataset and its corresponding model has its own ideal selection of layers to lock in order to provide for optimal watermark preservation. I also analyzed if the total number of parameters encrypted has an impact on watermark preservation. And from these 3 graphs, we see that there's little relationship between the two, regardless of the dataset or the trigger set designs. For future work, the framework used in my project could be applied to other data types, such as text and audio, as well as other machine learning models, such as long short-term memory networks, as well as other recurrent neural networks. Additionally, in my project, the locking mechanism focused on protecting the parameters in the neural network and further studies can be conducted to examine other locking strategies that aim to conceal information on the architecture of the model. Thank you.